In this example, we explore the properties of the motion and finding the velocity, acceleration, and the relative velocity and the relative acceleration of a rigid body. In this problem, we have an object of the BOC, which is turning around the point O, which is pinned down. And the angular velocity of this object is 2 radian per second counterclockwise, and the angular acceleration of that alpha is equal to the 3 radian per square second clockwise. All the dimensions are in millimeter, and we want to graphically find the velocity of the point B and C, the relative velocity of the point B versus C, the normal and tangent acceleration of the point B and C, and the relative acceleration. In order to do so, the first step is to find out the velocity of the point B and C. The velocity of the point B is equal to the radius times angular velocity, and that's a linear velocity of that point. Here, the radius of the point B, which is turning around point O, is equal to the OB, which is 60 millimeter, times the omega of the system, which is 2 rad per second. It is going to be 120 millimeter per second. Just make sure that the omega in this formula should be in the radian per second. The direction of that velocity is perpendicular to the radius of the rotation and in the direction of the angular velocity. As you can see, the VB is perpendicular to the OB and in the direction of the omega. Very similar to the velocity of the point C, equal to the radius OC times omega, the angular velocity, which is 40 times 2, 80 millimeter per second. And the direction of that is perpendicular to the OC and in the direction of the angular velocity, so it's toward up. The next step is to find out the relative velocity of the point B versus C. We know that the absolute velocity of a point is the velocity of that body or that point related to the somebody which is at the rest and it doesn't have any motion. But the relative velocity of one point is with respect to another point in that system. This is the formula of the relative velocity. The relative velocity of the point B versus C is equal to the absolute velocity of the point B minus the absolute velocity of the point C. Just as a reminder, this is a vectorial subtraction, not an algebraic one. In order to do this the subtraction, we can rewrite the formula in the format of the VB plus negative VC, which is a vector opposite direction, same amplitude or magnitude of the VC, which is going to be this one. The rest is to find out the vectorial addition of the VB plus negative VC, which we can use the tip to tail or any other vectorial addition basically method. This is the VB minus VC is going to result in the relative velocity of the B versus C. The next step is to find out the normal and tangential accelerations of the point B and C. The normal acceleration of the point B is the square of the linear velocity divided by the radius, which linear velocity of the point B is equal to 120 millimeter per second square divided by 60, which is the radius of the rotation, and equal to the OB, which is going to be 240 millimeter per square second. The direction of this vector is from the point B toward the center of the rotation and parallel to the radius of the rotation. The tangential acceleration is radius times the angular acceleration alpha. Here the radius of the rotation is OB equal to 60 millimeter times 3 rad per square second, which is the angular rotational acceleration of the object. And the resultant of that is 180 millimeter per square second. The direction of this vector is perpendicular to the radius of the rotation, which is here is OB, and is in the direction of the alpha, which is the clockwise, so it's going to be toward up. In the same way, the normal acceleration of the point C is equal to the square of the VC divided by the radius of the rotation, which is OC, which is going to be 160 millimeter per square second. And the direction of that is from the point C toward the center of the rotation O. And the tangential acceleration is OC times alpha, which is 40 times 3 radian per square second. It's going to be 120 millimeter per square second. The direction of the acceleration is toward the direction of the angular acceleration, and it's going to be perpendicular to the OC. The next step is to find out the absolute acceleration of each of these points. The absolute acceleration is the resultant of the tangential and the normal acceleration of each point. So we can add these two vectors of the normal acceleration and the tangential acceleration to find out the absolute acceleration of each point. So for the acceleration of the point B, we just need to add a normal component plus the tangential component, which is going to result to the absolute acceleration of the point B. And same for the point C, the addition of the tangential and the normal components of this vector is going to be the absolute acceleration of the point C. The last step is to find out the relative acceleration. Same as the relative velocity, we have very similar formula, which is the relative acceleration of the point B versus C is absolute acceleration of the point B minus absolute acceleration of the point C. Again, this is a vectorial relationship. On the other hand, we can write it down as the absolute acceleration of the point B plus negative absolute acceleration of the point C, which is an opposite direction vector as of the AC. This is the acceleration of the point B. This is minus AC. As you can see, the direction is opposite. It's a similar magnitude and similar direction, only the direction is opposite. And the addition of these two is going to result in the relative acceleration of the point B versus C.